So now that we've talked about all these different operators, like concurrency operators, scheduler operators, suppressing operators, action operators, and so on and so forth, let's show how to apply them in the context of the next round of case studies, which is a two-parter. Part one for case study ex2 is going to show how to use all the things we just talked about, plus some other things we've talked about before, to create large random big integer objects and asynchronously check if they're prime in a background thread from the default parallel thread pool. And this is actually super fun. We're also going to show off that mono from runnable operator here that we were just talking about. And as usual, you can get this in my live lessons GitHub repository in the reactive folder with the Flux subfolder in the ex2 project. So here we are in the ex2 project from the reactive Flux portion of my GitHub repository. Let's take a quick look at the ex2 driver program. As usual, this is the main entry point into the test program. You can see it's going to register two methods under test. One of them is called test_is_prime, which will test a stream of random big integers to determine which values are prime using an asynchronous time-driven Flux stream. And then we have another one called test_is_prime_async. I'm just going to talk about test_is_prime_timed right now. And then the next part of the lessons we'll talk about test_is_prime_async. As you can see, we register those with the task barrier. We run all the tasks, which will be launched to run in the background because they're asynchronous. The main thread blocks so it doesn't fall off the end before the asynchronous tasks have a chance to complete. And when we're done, it'll return the number of tests that completed successfully, and we'll print that value out right here. So let's go take a look at test_is_prime_timed. So a couple things to note. First, this is part of the Flux EX class. We got a bunch of fields here. We got one that keeps track of the maximum random number value because we're going to generate 10 million values. We're going to have 10 iterations. We're going to see how that gets used here in a second. We're going to generate some random numbers that are going to start with a lower bound and going up to a max bound. The lower bound is the max value minus the number of iterations. And we're doing this in order to be able to get some duplicates. Then we're going to create a memoizer. Memoizer is a design pattern that's used to cache values that would otherwise take a long time to compute. So the first time that you need to compute them, you do in fact run some creation method to do the job of initializing something. And then henceforth, that value will be stored in the cache. And next time it comes along, we just look it up and don't have to recompute it. What we're computing here is prime numbers, so those could be large, very long times to run because we've got a lot of large values. And so this is going to cache the results of numbers to see what their prime factors are, or prime factor is. So that's a concurrent hash map. We'll talk about that when we get to that. We have a random number generator. We have a field that keeps track of the duration to sleep for the Flux interval operator. We'll talk more about that. And then down here, we have a predicate that only matches odd numbers. So this takes mod of the value by 2 and see if it equals 0, and we negate that. And then the final thing we have here as a field is something called sGenerate big random integer. And this is a lambda expression that generates a random big integer. And we do it from lower bound up to the max value. So again, we're trying to generate some duplicates. Let's go take a look at test_is_prime_timed. First thing we do is we make a string buffer. We've been using string builder up to this point because it worked with a single thread. We only had single-threaded code before. Now we've got multi-threaded code, so we use string buffer because string buffer is thread safe. So multiple threads can be adding things to a string buffer, and it won't have to worry about corruption. We then create a callback that will write a big integer to the string buffer. So we can see, we just go ahead and print this. There's a little helper method called print. You can see it just goes ahead and emits it into the string buffer. And then we make ourselves a Flux stream. And this is super cool because we're going to show off a couple different features we've talked about. Notice we're using Flux create. Remember, Flux create is this dynamic factory method. And we're going to give it the result of calling make timed Flux sync. So what is make timed Flux sync? Make timed Flux sync is a factor method that we use to bridge the reactive world with the callback style world. So it'll emit a time-based flow of random big integers at periodic at a periodic interval. So here's what we do. We're going to return a consumer to a Flux sync. And here's what we do. This is just good old Java lambda expression syntax. We could, if we were so inclined, convert this into some other format. Let's see if I can get it to do some other format that's interesting. Let's see. So you can extract it into a method reference if you want, but we're not going to do that. We're just going to keep it the way it is. So we're going to have a Flux that will generate values starting at 0 every half a second. So every half second, that's what sleep duration is. It's going to generate a value starting at 0, 0, 1, 2, etc. We're then going to convert this thing into this generate max random big integer. So it's going to, at a regular interval, it's going to generate a random integer. And then we're going to filter out even numbers to ignore them, so we only allow primes. We're then going to only take S max iterations of these things, which they're 10. So we're going to get 10 random big integers. And then we're going to use the subscribe operator to say, hey, Flux sync, emit each of those 10 values, followed by the complete signal. So this will basically emit these 10 things. And interval runs in a background thread. So this is going to take place in a different thread than the other threads we're about to use. So as you can see here, we're going to generate a Flux, will generate a Flux that will emit random big integers, 10 of them every half second. Now, back over here, we're now running in a different thread. This is in the main thread, so it's a different thread. And what we're going to do is we're going to log the values that come through. We're then going to go ahead and check to see each of those big integers, whether they're prime or not. So we call this little helper method. And this helper method is just so freaking cool. It's going to use the ConcurrentHashMap compute if absent method, which is an atomic check then act method. Very, very, very powerful. And what it does is it says, if prime candidate is not already in the concurrent hash map with a value, then and only then atomically check to see if the value is prime and add it to the map, add the result of the prime check to the map. The prime check is just a very simple method that could actually take a while to run, but it's very simple. It just goes through and tries to see whether this value is a prime number or whether it has a factor. And if it has a factor, it picks the smallest factor if it's not prime. I won't go through that code, but if you know what prime number checking does, this is an intentionally very inefficient way to do it, just to burn time. So the first time through, we compute whether the value is prime or not, and then we store that into the concurrent hash map. And any subsequent time compute if absent is called, it'll determine that the prime candidate already has a value, namely either 0 if it's prime or its smallest factor if it's not prime, and it'll just return that value there. So that is what's called a memoizer. Very useful technique to understand. So we do that. What we end up here coming out of this thing will be the results of check if prime, and then we will have a method, an action operator that will process the result. And what it basically does is it just takes the result that came back here, which is this thing called a prime result, which is just a Java record, which keeps track of the prime candidate and the smallest factor, which is either 0 if it's prime or the smallest factor if it's not prime. It'll print those results out if we're in debugging mode. And then the very, very, very final thing we do in this stream is we will display the results, which we get out of our string buffer, and they'll be printed. And then we're going to return this then operation. And if you look at display, see, it just prints the results. And this will then just return an empty mono that informs the async task barrier. This asynchronous computation is done. OK, so that's what happens with this stuff. Now, I had run this before, and here's the results. Now, what's interesting is we have two different methods. We haven't talked about the second one yet. Test is prime async, and test is prime timed. And we'll talk about this when we get to the next walkthrough of the test is prime async method. We'll talk about this next in the next part of the case study lesson. But here's what happens for test is prime timed. You can see that every half a second, it emits an odd number. You can see that is being emitted, and that's coming from this parallel thread from whatever Flux interval is using. And it'll then check to see if it's prime, and we'll print that out. And what you basically what's happening here is all that processing is taking place in the background thread, which is the interval thread. You can see it's all parallel 1. That's the background thread that the Flux interval is using. There is no other thread that's being used. So this will just basically check to see whether things are primed. And you can see we explicitly check. And if we found something that was already in the concurrent hash map, it wouldn't have to explicitly check to see if it was prime. It would look it up and know it was already there and get the value back. OK, and it doesn't look like there are any non-prime numbers, but that would just depend on the randomness that we generate. So that is the first case study.